We are starting lesson 8.3, which is estimating with confidence, and we are estimating a population mean. So make sure you have your notepad with you, make sure you have your formula sheet with you, because we're going to learn about a new table, and make sure you have your calculator with you. And look down below, you'll see where I'm at in my calculator to kind of help us out. So as we go forward, what this does, and some things might seem a little familiar based off of 8.2, but we're going to construct and interpret a confidence interval for an unknown population mean, hence estimating a population mean. We're going to determine the sample size required to obtain a certain level of confidence for a population mean with a specified margin of error. We've talked about margin of error. Describe how that margin of error for a confidence interval changes based off of the sample size and the level of confidence. And then determine sample statistics from a confidence interval. These are the four things we're going to address, which is a lot. So if it's a lot, I think we need a map to kind of help us out to figure out what we're going to do. And well, that map for us is our AP decision tree. And if I were to go through and think about this, where we start is we have a population parameter. Now, we don't know it in this chapter. We're estimating an unknown population parameter. And in the last section, we dealt with categorical variables, which gave us the ability to say, hey, in 8.2, we had an unknown population proportion. In 8.3, that is where we're looking at a mean. We're looking at quantitative variables. And in this one, we have an unknown population mean mu. And right away, you can see there is a branch, two branches there. And what that tells us is we're going to be asked a single question. Do you know your population standard deviation, sigma? If it's given to you in the prompt, then you have scenario 1, where you know what sigma is, and we're going to do a one sample Z interval to find the population mean. Now, if I don't know what my sigma is, what the population standard deviation is, then I'm in scenario 2. I'm down here. And in that case, I'm going to do something new. I'm going to do a one sample T interval. So that is a new type of interval. So you can see how this decision tree is going to help us. And it looks like the most important part is that red. Do you know the population standard deviation? That question determines the path you go, so knowing how to read the prompts is key. So now we're looking at scenario 1 where you have your population standard deviation is known. So we would be doing a one sample Z interval for mu. And in this case, we're going to go back to an activity that we did in 8.1 where we had the mystery mean average for the semester exam. And that's where I got this information from. So you can go back to the notes or watch the previous video for 8.1. And what we have here is we are creating a confidence interval based off a sample mean that I got. And in this scenario, I had a sample mean of 88.5%. I had a sample size of 13. And the standard deviation, since Mr. McNichols and I gave the exam, we know the standard deviation was 8 for the population. So we knew the population standard deviation before we did this activity with you. So you can see here for the confidence interval, I still have it highlighted. The way we've been doing is your estimate. And remember, your estimate is an unbiased estimator. And that was what chapter 7 was about. And since I want to estimate my population mean, my unbiased estimator, since I don't know mu, is going to be X bar. And so I'm going to use X bar, which in my case was 88.5. Plus or minus your critical value, which in this case is going to be a Z star, and times your standard deviation of the statistic. And together, when I do those, I'm going to get what we call the margin of error when I multiply them. And so I have my Z star, and in this case, if I'm constructing it, I'm going to do a 95% confidence interval. So I'm going to use 1.96, or I could use 2 if I'm applying the empirical rule, about 2. The standard deviation I told you since I gave the exam was 8, and my sample size was 13. So you can understand that. So when I find the product of 1.96 times 8 over the square root of 13, that by itself is my margin of error. And so when I have that 4.35, that number represents the margin of error. And so here's really what's going on. You can see that sampling distribution down below. And what's going on is I have some X bar, 88.5, and I don't know what mu is. Okay, so we don't know what this average was on the exam. And if I'm looking at it, I go, fine. If I have a margin of error of 4.35, what that means is I'm going to go to the left and to the right 4.35 units away from the 88.5. And that's where I got the numbers of 84.15 and 92.85. And so that's really what we're doing. If you look at it, this one actually, if that distribution is the graph I'm supposed to have, that is I captured it. I captured the population mean. So here's what we have now. So this is really the general setup is, if you're dealing with scenario 1, you're going to use Z star because the population standard deviation is known. Do not ignore all the writing down there. And that writing down there is extremely important. Choose an SRS. So if I'm looking at choosing an SRS, what's really important to know is that's your random condition. You are addressing the random condition on that. So when you're reading this, be careful what it says. Even then, it says an unknown mean mu. Isn't that why we're doing confidence intervals? It's because we don't know our population mean. We're trying to estimate it. And then I also have the idea of, okay, I need to figure out my normal and my independent. As long as the normal independent, and those two are your conditions. Those are things we have to look at as well. When those work, when those conditions are met, that's when I'm going to use the formula. X bar plus or minus your critical value times the population standard deviation divided by the square root of your sample size. And the critical value Z star is found from your normal distribution. So this slide, notice all the markings on there. This is your scenario 1. And really it's only one slide for scenario 1. And the question is, well, why only one slide for scenario 1? And here's my notes. And really you could pause and kind of write down some of the stuff. But I really took a picture of this and put it on here because I want you to see the red. That if we are using a confidence interval to estimate an unknown population mean, we really most likely do not know the population standard deviation. Because think back to the standard deviation formula. And that's what you see over on the right there. Standard deviation is, the distance of your data from the mean squared divided by n minus 1. You look at it, well, if I don't know mu, if this is completely unknown to me, then how can I find my population standard deviation? And so it's very, very rare to know the population standard deviation without knowing the true population mean. And that's kind of why we have only one slide here, is because this scenario 1 is a very rare thing. Because if I know my population standard deviation, I probably know my population mean because I had to use that to find the population standard deviation. So this part just meant to go through this slide 1, this scenario 1 for you. So now we're on your slide 3, and this one deals with choosing the sample size. And you can see here that I labeled your critical value times your standard deviation of the statistic as your margin of error, ME. And what's really important on this slide that we don't see when estimating a population proportion is that we can determine a sample size for a desired margin of error. And you can see how I have those two things highlighted. And here's why this is amazing. This is why I love this one, is you think about this. If you are conducting a study or an experiment and you're trying to figure out what is the minimum sample size that I need if I'm willing to accept a margin of error of, let's say, 3%. I can put 0.03 in. And if I set my confidence level, I can solve for the sample size. And that will tell me the minimum sample size needed so that way I don't exceed that margin of error. And so if you think about when you are setting up for a study, that's a crucial thing. I'm willing to accept a 5% margin of error. Okay, what's the minimum sample I need to collect? It helps you with setting up and organizing the study. So again, I digress, but I think that's really important to understand is notice how that's worded. The desired margin of error. So that was determined before you performed the study. So that way you knew how many your sample size to collect. So to determine a sample size, there are a few things you can do. You can get a reasonable value for your population standard deviation from an earlier or a pilot study that was done. You find the critical value, your Z star, from the normal curve based off the confidence level that you're willing to accept. And then set the expression of the margin of error to be less than or equal to the margin of error and solve for n. So we are going to do this, and we're going to look at how we go about doing this. But before we do this, I do want to show you something else that I think is important to understand about margin of error. And so you can see right here, I have a population distribution. And for that population distribution, I do not know mu. And that is the population distribution, and it just happens to be normal. Amazing. But I don't know it. So I'm going to construct a confidence interval. And when I do that, and I say I do it one time, right there is my first one. And that, you can see that interval is pretty small. And I missed the population mean. Darn. So I did it again. This time, I captured the population mean. Yay. And what's really interesting about that one is notice the interval is a lot larger. And that's what I want to address with you with margin of error. So when you have an interval that is small, if you think about that, the distance from here to here, that is your margin of error. So that's a small margin of error. Here to here, that distance is your margin of error. That's a large margin of error. Now, when you have a small margin of error, you can either have a low confidence level and or a large sample size. And it's not that it's I go and both. Is I can have a low confidence level. If I threw a net that small into the ocean, there's a very good chance I'm not going to catch anything. And that's the idea. It's a low confidence. I'm just throwing things small out there, and hopefully I get it. Who knows? But if I throw a huge net out there, I'm bound to get something. I'm covering more area that way, more probability under that distribution curve. So when you have a large margin of error, you have a high confidence level because you have a larger net. You're pretty sure you're going to catch something. So you can have a high confidence level and or a small sample size. But the small sample size, you're going to have a huge margin of error. There's going to be huge variability with a small sample size. So it's something to keep in mind here before we do these examples with margin of error on how it can affect the either sample size or your confidence level, how those two things can affect that margin of error. And so now we're looking at an example of how to find the sample size for a given margin of error. This is how many monkeys? So researchers would like to estimate the mean cholesterol level, mu, notice words and symbol, of a particular variety of monkeys that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter. Within, doesn't that sound like that's your margin of error? And then so the true value of mu at a confidence level of 95%. A previous study was done, and it suggests the standard deviation of cholesterol level is about 5 milligrams per deciliter. So notice it says a previous study, so that's kind of telling us what we're going to be using for our population standard deviation. That was talked about previously when we looked at the different ways to work with your margin of error. So if I have a 95% confidence level, we want to figure out what is our critical value, what is our Z star. You can use the inverse norm in your calculator. You can use also your table. We discussed this. Is right at the bottom there. You can see we said, hey, where it's infinity, label it Z star. And at 95%, I notice right here, I have a 1.96. Or I can estimate it by applying the empirical rule of 2. But I'm going to use 1.96 here because I can. So in this case, 1.96. And when it says, hey, we're going to use a sigma of 5, that is our best guess for the standard deviation because it was from a previous study. And that was addressed before we looked at that box with the margin of error criteria. So when I set this up, and we have our formula, and the formula is your Z star times your population standard deviation over the square root of n less than or equal to your margin of error. Okay? So that's what I have there. Now you apply your algebra skills and you solve. And so what I'm going to do is I'm going to move the radical end to the other side, but at the same time, I'm going to multiply the 1.96 and the 5 together, and that's going to be boom, 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 boom. So I have my information here. And so when I multiply those, it's going to give me the information, and then I'm going to square it. And so in this case, I believe I would take 1.96 and I multiply that by 5. I'm going to get, I believe it's 9.80, so 9.8 square root of n, and I'm going to square both sides. And that's going to give me the information. So what I'm going to do is I'm just going to go right here where the work's already typed out for us. And when I do that, I'm going to get 96.04. And so look at this. Your n has to be larger than 96.04. So in this case, I am going to round up to 97. If I round down, I am, in that case, not hitting my threshold for margin of error. I'm going beyond what I want. So I need to go and making sure I get above it. So you're going to round up. You're not rounding to the nearest, you're rounding up. So, man, that'd be a great multiple choice problem, wouldn't it? Like, choice A to be 96, choice B to be 97. That'd be a really cool multiple choice problem to see if you're paying attention to this idea of rounding up. Now, there is that box up there that you see is the sample size determines the margin of error. The sample size. Well, how do you know that? Awesome question. Glad you asked. Because it's in the formula. That's how I know. The sample size determines your margin of error. The size of the population does not influence the sample size needed. Say it with me. The size of the population does not influence the sample size needed. It's the margin of error that influences the sample size needed. And so in this case, we have our margin of error. And so you can see we round up, same thing we did with our population proportions when we did the margin of error. Now you have this part right here. Check your understanding. And so, again, take one moment, pause the video, read it, underline what you think you're doing, and see what is being said. So, pause. I'm kidding. You just please pause. Well, in the amount of time it took you to do that problem, I was able to move to the other side of the computer screen. So in this case, here's what I want you to get. Is notice we did not know our population standard deviation, and that's something important to keep in mind. Is what we're going to do is we are going to use information from a previous study. And so if I'm going to mark this when I read it, I'm going to go ahead and highlight that in a previous study. So though our population standard deviation was not known, a previous study told me, hey, it was 0.0002 grams. And so since our sigma is unknown, we're going to use a reasonable value from the previous study to help us out. Now, how many measurements must be averaged to get a 98% confidence level for it? And a margin of error of 0.0001. So that 98% confidence level, what that does is that tells me to go find my critical value Z star. And so when I did that, I had my 2.33. And so that's where I got that value. And I'm going to multiply it by my population standard deviation divided by the square root of the sample size I'm trying to figure out. Now that has to be less than or equal to 0.0001, the margin of error. And I want you to realize kind of what we're going through and what we're doing here. And so what happens is you have some X bar that you're going to find after you collect the sample, okay? We don't know X bar yet because we haven't collected the sample. We're trying to find what our end value is. So we're going to figure this out. Now, what's going on is I'm willing to go to the right and to the left of that value, a margin of error of 0.0001. So I'm going to add and subtract the 0.0001, that margin of error, to my X bar. Now remember, that margin of error is your critical value times sigma over the square root of n. That's really what you're doing as a diagram there, as you can see it. So kind of always know what you're looking at here. And so we have that information, and it's kind of going through, and if I would do that, I would have to round, and I would get my sample size to be 22. So hopefully your algebra skills on this one, you're going to have to show some of the work for it, and you can see that it is going to be 22. And so now we're on your slide 7. In this case, we're looking at scenario 2, which is when you do not know your population standard deviation, when it's unknown. And these create something called a t-distribution. This is a really, really, really important concept because, again, if you don't know your population mean, then you probably don't know your population standard deviation. We talked about that earlier. So t-distributions are going to occur quite often. So this is a scenario 2 is pretty important. So when we don't know sigma, we can estimate it using a sample standard deviation S sub x. Now, why? Because the sample standard deviation is an unbiased estimator of the population standard deviation, chapter 7. So when this sampling distribution of x bar is close to normal, we find probabilities by using that whole formula, z equals x bar minus mu over the square root of sigma over the square root of n. But what if we don't know sigma? What if I don't know this? And notice, you do not know sigma. It's right there in the title of scenario 2. Well, in that case, what we can do is we can use our sample standard deviation. We can use S sub x. Now, what happens when we standardize with that? Because it's not the population standard deviation, it is the sample standard deviation. Well, in that case, a new statistic is created, And that new statistic, and this is really important, does not have a normal distribution. Does not have a normal distribution. T distributions are not normal distributions because they're created by using a sample standard deviation, not the true population standard deviation, because that's unknown. So that is a really big thing right there, is that the new statistic does not have a normal distribution. So what type of distribution does it have? And you can see I have a lot of information here already written out for you. Some of them you have to fill in, others you might want to go ahead and start writing down and listen, because a lot of things we say is going to be important. When you have this, and you see right here there are two dot plots. You have the top one, which is your T distribution, the bottom one, which is we'll call it your Z distribution, the population. And when we go through, realize there are some things that they have in common. They have a different shape. Right away I can see that one of them has more spread, the T, than the Z does. However, something it does have is they are symmetric. They're both symmetric. And it has a single peak at 0, just like our normal distribution. So at least it has that. It's symmetric and it has a single peak at 0. However, something that's really interesting, and I have it right here for you to fill in and I'll show it, is there is more area in the tails of a T distribution. And so I'm going to just focus right here, is if you take a look, the top one is your T and the bottom one is the Z, and I'll label it here and here for you to kind of see it. Notice there is more dots in the tails of the T than there is in the Z. So right away I can see that. There's more observations or more area in the tail, and that is the purple part right here. There's more observations, there's more area in the tail. So what else? I could see also, based off of it, there is a large spread based off of T distribution sometimes. And we'll figure out how we can get that spread to not be large. And that's really important, is there's times where it is going to be. It's going to be larger than a normal. Not large continually, but larger than normal. And then, one thing too is it has less observations in the center. So pay attention to this. If I were just to draw a vertical line here, and I'll try and put it on one standard deviation to the left, and I'll try and put it on one standard deviation to the right, is notice there's more in the center part of a Z distribution, a normal distribution, than there is in the T. Because in the T distribution, there's more in the tails. In the Z distribution, there's more in the center. So we look at these formulas. Keep in mind, the T formula looks very similar to the Z. X bar minus mu. Same numerator. That's good news. However, the denominator is you're going to replace sigma with S, because this is an unbiased estimator of your population standard deviation, which is unknown. So keep that in mind here. So like any standardized test, it tells us how many standard deviations it is away from the population mean mu. One thing that is new, and this is really important, is that there are different T distributions. There's one normal distribution. There's one normal distribution. There are different T distributions, and those T distributions are based off of your sample size. So again, sample size is crucial for T distributions. And what happens is we determine which T distribution we are using by stating what we call the degrees of freedom. And so make a note that your degrees of freedom are going to be linked somehow, we don't know yet, to your sample size. And when we do this, this determines which T distribution that we are dealing with. And again, that's something new. And what's going to do is I'm going to go ahead and I'm going to show you an applet that goes through the T distributions to make more sense. So you can see over here I have the website Our Psychologist, and they have an interactive T distribution to compare to the normal distribution. So in this case, our T distribution, if you look at the legend there, is the blue curve. Our normal distribution is the dashed curve. And the first thing to take a look at it is, you can see as I make adjustments, is what I just did is I have it finding the area in the tail. And if I zoom in right here, notice the area in the tail for the T distribution is 0.063, while in the normal it's about 0. And the reason why is because when you look at it, you can see as we go through. And really it's because you have no sample. So you have a sample size of 2. So really, let me do this. Let's see what happens, and we'll look at this first, as I increase my degrees of freedom. So right now I have a sample, degrees of freedom of 1, so I'm going to increase this. And notice, as I increase, what happens to the shape of the t distribution. And what happens is it becomes closer and closer and closer and closer to that dash distribution, the normal distribution. So as I increase my degrees of freedom, the closer I am getting to a normal distribution. And look at that area in the tails. Yes, there is more area in the tail for that t distribution, 0.078, but notice how it's pretty close to the normal distribution, 0.076. So as I increase my degrees of freedom, I'm actually approaching a normal distribution. I'm not equaling a normal distribution. I'm approaching a normal distribution. It becomes approximately normal. And so we can see that's the first thing. And we can see the tails here as well. And so as I increase my degrees of freedom, then it becomes approximately normal. But as I have a smaller degrees of freedom, the worse off I am. And this is almost, 0.076 compared to 0.05. That's a pretty big difference in there. And so we want to make sure we can see that there's more area in the tails there based off of the degrees of freedom. Now, one thing that we can't see because you're dragging is the first thing we talked about in the previous one is there's not one t distribution. There's many, many t distributions. And think about that for a second. Every time I slide this, a new curve is created. Every time I change my degrees of freedom, a new curve is created. I change my degrees of freedom, a new curve is created. I change it again, a new curve. So there is not one t distribution. There are many, 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 many t distributions. So keep that in mind. And that was the idea behind what we looked at in our notes, is that we have not just one. The t distribution is determined from your degrees of freedom. So keep that in there. There's not one like there's a normal. There's many, 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 many t distributions. All right, so let's look at your slides 9 and 10. When we perform inference about the population mean mu using a t distribution, the appropriate degrees of freedom, and we use the symbol df for degrees of freedom, they are found by using the formula your sample size minus 1. That tells you your degrees of freedom. N minus 1 is your degrees of freedom. And we can use also another notation to tell the reader to communicate which t distribution we're using. We can use a t with a subscript. And you really look at your t with your degrees of freedom. And that counts as, hey, I'm using a t distribution with degrees of freedom. And in this case, hey, I'm using a t distribution of degrees of freedom of 42. Okay, so that tells the grader that I have degrees of freedom of 42, and that's the t distribution. So we can use that subscript to help us as well. So when we are looking at a t distribution with degrees of freedom, draw a simple random sample of size n from a large population. I wonder what that means, a large population, with a mean of mu and a standard deviation of sigma. What happens is the t distribution follows this formula. It is your sample mean minus the population mean over the standard deviation statistic from the sample divided by the square root of n. And we have degrees of freedom again of n minus 1. So the statistic will have approximately a t distribution of n minus 1 as long as the sampling distribution is close to normal. So we have previously looked at in chapter 7 what tells us whether a sampling distribution is approximately normal when we deal with means. It looks like maybe it's random. Maybe we have the central limit theorem to help us out as well for that. Maybe we look at, if we're not sampling with replacement, we're sampling without replacement, the 10% condition. Doesn't that tell us whether our sampling distribution is approximately normal? The stuff from chapter 7. So here's a couple things to keep in mind with t distribution in degrees of freedom. And we're comparing the density curve. There are several things to keep in mind. The curves of the t distribution is similar, not the same, similar to the shape of the standard deviation normal curve. That's important, is they are similar, they are not the same. Something else to keep in mind is that the spread of the t distributions is a bit greater than that of the standard normal distribution. So it is a little bit greater. Again, it has a larger spread, and I talked about that. The t distribution also has more probability in the tails and less in the center. We talked about that one already. And one thing to keep in mind, this is what the applet showed us as well, is that as you increase your degrees of freedom, the density curve approaches the standard normal curve. It doesn't equal it. It approaches it. And so it becomes approximately normal. So you can see that stuff here, and you can see, and the applet kind of showed us what was going on. I'm going to kind of, you can see what I wrote down here, if I zoom in a little bit, is the smaller the degrees of freedom, the larger the area in the tails, and the smaller the area in the center. So the smaller the degrees of freedom I have, the more area I'm going to have in the tails, and the less area I'm going to have in the center. The larger the degrees of freedom I have, now I'm going to approach the normal distribution curve. Now we can use, in the back of the book or on our formula sheet, table B to help us find our degrees of freedom, or we can use that calculator up above, and again, notice where I'm at in that calculator to help us find our t distributions based off of a degree of freedom. And so now we're looking at the example of finding the critical value for t star. And in this problem, we're looking to use table B based off constructing a 95% confidence interval for an unknown population mean mu from a normal distribution using a simple random sample of size 12. What critical t star should we use? And so we're going to try using that table B over there. And when we have this, let's go to table B. And we're going to consult the row that corresponds to the degrees of freedom of n minus 1. And so my degrees of freedom in this case is going to be 11, because I have to do the 12 minus 1, and that's going to give me my degrees of freedom. And so I'm looking here. This is the row I'm going to go to. So that's the row I'm looking at. Now what we're going to do is we're going to move across that row until it corresponds to the 95% confidence level. And so I look on that bottom part, I can see here's my 95% confidence level. And so right here is where I'm looking. And so right away I can see what my t star value is going to be. It's going to be 2.201. And so right here, what I did is I found my degrees of freedom to be 11, and I moved across, and I got a t star value of 2.201. That's how you use your table B, is you go to your degrees of freedom, you find the confidence level you want, and you see where they intersect. So that's table B in a very, very simple way. And we're going to try a couple of them, and it will slowly get harder as we do the next few examples. So now we're on your slide 12, and we're going to be using table B to find the critical value. And by the way, we're going to use our technology, the calculator down there, for one of them as we go through. Now, when we're looking at this, let's just kind of make notes. Is we want to construct a 98% confidence interval. So we need to find the t star for that based off of 22 observations. So I have my confidence level, check. Now I need to figure out what's my degrees of freedom. And in this case, my degrees of freedom is n minus 1, it's 21. And so really what I'm doing is I'm finding the t star value based off of a degrees of freedom of 21. Remember, I need to specify the degrees of freedom. You have to always specify the degrees of freedom because that has a specific shape to it. And so what I'm going to do is I'm going to go to my table B, and I have a degrees of freedom of 21, and I have a 98% confidence level. And right away I can see 2.518. And so that is the t star critical value there. The degrees of freedom of 21, I'm at the 98% confidence level, I find where they intersect, and I get 2.518. And I'm going to use those rows and columns to slide around to get the next one. Now, a 90% confidence interval, so I have my confidence interval, check, with a degrees of freedom of 9. Do I need to do n minus 1 here? And the answer is no. You don't need to do n minus 1 here because you already know your degrees of freedom. I can say right now what I'm trying to find is I'm trying to find a t star value of 9. By the way, what's my sample size here? What's my n? And in this case, my n would be 10. So it's one of those things where you don't need to subtract in this case because I gave it to you. So I want a 90% confidence interval with degrees of freedom of 9. And so I'm going to take this, I'm going to slide it up. So I want 90%, and 90 would be the 1, 2, 3, 4, 5, 5th column. So 1, 2, 3, 4, 5th column. And I want degrees of freedom of 9. And so in this case, it looks like I have 1.833. And so I have 1.833 as my t star value. Now, I wanted to construct a 95% confidence interval, so I have my confidence interval. Good, I can go to that bottom part and take a look at it. Now I know my sample size is 7, so I need to state what my degrees of freedom are, and there's 6. You always need to state those degrees of freedom. Always, 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 always. So I'm trying to find a critical value, a T star, that is based off of degrees of freedom of 6, because remember, each degrees of freedom has its own T distribution, so I have to specify that degrees of freedom. So I'm going to take my degrees of freedom, 6, boom, 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 and I'm going to take a look at what was my confidence level. I want a 95% confidence level, and so I believe a 95% confidence level would put me right here. So 1, 2, 3, 4, 5, 6, good, and so it looks like it's about 2.447. So 2.447 is where they're going to intersect. Perfect. I can use that to help me. So last one, here we go. 99.8% confidence level, check. N equals 1,000. Awesome. That means my degrees of freedom is 999. That's a pretty good degrees of freedom if you ask me. So I want to find wait a minute. There is no 999. So here's where things get a little interesting if you're using table B. If you go and you use table B, there are gaps in there. It jumps from 30 to 40 to 50 to 60 to 80 to 100, all the way from 100 to 1,000. There's not a 500 degrees of freedom row in table B. So what do you do when there is a gap? And so when there is a gap and your degrees of freedom falls in that gap, what you do is you need to go to the previous one. So even though I have a degrees of freedom of 999, if I'm using table B, I have to use 100. Because I can't say I have a larger sample size than I really do. If I say 1,000 is my degrees of freedom, that means I had a sample size of 1,001. And I can't say I have more people in my sample than I really have. So we have to go down to the previous row. So if I had a degrees of freedom of 47, yay, congrats, it's close to 50, but you know what? You're going to have to go down to 40. And so that's kind of something that would be a little bit of a flaw with your table B, is if it's not in the table, what do you do? And what we can do is we can use our calculator to help us. And so you can see right down below where I'm at. I'm in my distribution, so second vars, and that's where you can go. And notice number 4 says inverse T. So I can hit enter on inverse T. And it's asking for the area. So what do you think that area is? Well, based off of what I see in table B, it says your tail probability. You know, how much area do I have in the tail? And notice it's asking just for one side of the tail. And so in this case, if I have a 0.998, so if I have a distribution, boom, and I have my normal distribution curve, and I have in the middle 0.998, in between, in each tail is 0.001. That's how much space I have in each tail. So something tells me, based off that picture, it's trying to tell me I'm going to use 0.001. Boy, I hope I'm right. And I'm going to do a degrees of freedom of 999. And I'm going to hit paste. So if you don't have that prompt feature, it's inverse T, degrees of freedom at the very end, but first input your area in the tail. And you're going to go 1 through, so 0.001, one tail, and you're going to have 999. So if I hit enter, in this case I get negative 3.09841. So what does that mean? Well, that's telling me this part, negative 3.098. Well, remember, they're symmetric. And so this would be 0.3098. And so I have a T star value when I have 999 as my degrees of freedom of 3.098. Well, let's check it out. Let's see what's going on. If I have a 95%, so if I have a 95%, how much area is in the tail? And I could have 0.95 here, and 0.025, and 0.025. So what's interesting is if I go to my, same thing, second distribution, inverse T, number 4, This time, you know what I'm going to do? I'm going to change. I'll do the same thing for this one. I'll go area to the left, 0.025. And my degrees of freedom here was sample size of 7 is 6. So if I hit enter here, this one gives me negative 2.4469, which 2.447. Again, this is giving me the negative. We're like, well, Mr. Rainsberg, why is it giving you the negative? Good question. Because I'm using the area to the left, and I'm telling it I only need this one. If I wanted, and I'll use this one instead of going back to the previous one, if I wanted the positive critical value, the positive T star, I would take my 0.95 and I would realize what we're doing is we're adding these together, and that would be 0.975. So I wonder if I do 0.975, what's going to happen here? And look at that, it's the same thing with positive. So remember, it's symmetric. So if you get the negative, you're going to use the positive for it. And that is the end of slide 12. And it's the end of part A for lesson 8.3.